You ever wonder how people survived, extreme climates for thousands of years without a single watt of electricity? Well, in this explainer, we're going to uncover the hidden genius in ancient buildings. It's a story where old world wisdom meets some pretty hard modern data.
I mean, really think about it. In a world without that instant fix of a thermostat, how did people in these sweltering humid jungles or on cold, damp mountainsides actually stay comfortable? How did they not freeze in the winter or just roast in the summer?
And the answer, as this research so brilliantly shows, is that they weren't just tougher than us. They were smarter builders. Their homes were these incredibly sophisticated, climate-responsive machines, engineered over generations to work with nature, not against it.
So, what's the core idea behind these amazing structures? Let's dive right in.
Okay, so there's a name for this, right? It's called vernacular architecture. And it's really just a fancy way of saying you build with what you have, where you are, for the life you live. This isn't about some grand design from a faraway architect. It's all about practical, local solutions that get passed down.
So what's the logic here? I mean, what makes this type of design so intelligent? Let's break it down.
It really boils down to a few key ideas. You use local materials because they're already perfectly suited for the environment. The design itself is a direct response to the climate, whether that means you're trying to catch breezes or trap sunlight. And this concept of bioclimatism, which just means designing to take advantage of the natural climate, well, that's at the heart of the whole thing.
And think about what that means for us today. By using materials you find right on site, mud, stone, wood, you completely eliminate the huge energy costs of manufacturing and transportation. This is sustainability in its purest, most original form.
Now, to prove this wasn't just some, romantic notion, a team of scientists actually put this theory to the test. They went to Northeast India and studied 2 different vernacular homes in 2 radically different climates. Okay, so take a look here. These are the 2 locations. We've got Tezpur, which is in a warm and humid zone, and then we have Cherrapunji, up in a cold and cloudy highland climate. Same region, but completely different environmental challenges. And let's be super clear about how different we're talking. Tezpur is hot and sticky. Your main goal there is just to get air moving and stay cool. Cherrapunji, on the other hand, is one of the wettest places on Earth. It's often cold and damp. The goal there is to stay warm and dry. 2 totally different problems.
And this is where you can really see how form follows function. In warm Tezpur, the goal is ventilation, so the house has these huge openings, almost half the floor area. But in cold Cherrapunji, the goal is to conserve heat, so the house is way more compact with smaller openings. Every single detail, the materials, the shape, the windows, it's all a direct answer to the local climate.
So these houses look like they should work, but do they? This is where the science comes in. The researchers didn't just look at the houses, they measured them rigorously.
For a whole year, through winter, spring, summer, and fall, they set up data loggers inside and outside both homes, recording the temperature and humidity every 30 minutes. This gave them an absolute mountain of data to see exactly how these buildings performed in the real world.
Okay, let's look at the results from the warm climate first. That jagged pink line you see? That's the chaotic swing of the outdoor temperature. But look at the blue line. That's the temperature inside. The house acts like this massive thermal buffer, just smoothing out those extreme peaks and valleys. It's literally taming the climate.
And now for the cold climate. It's the exact same principle, just with a different goal. The outside temperature is all over the place, but inside, the house maintains a much more stable and warmer environment. It's holding on to heat instead of just shedding it.
So here's the bottom line. Across both of these completely different climates, the thermal mass of the local building materials cut the daily temperature swing in half. That is incredible performance from just mud, stone, and wood. No furnace, no AC, nothing.
But the researchers, they wanted to go one step further. Was it possible to understand this performance so well that they could actually predict it? Could they turn this ancient wisdom into a mathematical formula?
So they took all their data, the outdoor temperature, the humidity, but they also added a really critical variable: people. They tracked how the families opened and closed windows, when they used fans, and basically just how they lived in the space. And what they found was profound. How the people used the house, when they opened a window to catch a breeze or closed a door to trap heat, that was even more important than the materials the house was made of. These aren't just passive structures, they're dynamic systems that need human interaction to work best.
So after crunching all the numbers, they came up with their predictive formulas, and the result was this, an R-squared value of over 0.96. Now, in simple terms, that means their formula could predict the indoor temperature with over 96% accuracy. Wow! They had basically cracked the code.
And if you want to see what that looks like, check this out. The solid red line is the temperature they actually measured inside the house. And the floating dots, that's what their formula predicted the temperature would be. It's an almost perfect match. They had successfully translated ancient, intuitive design into the precise language of science.
Okay, so why does any of this matter for us, living in our world of concrete and steel? What can we possibly learn from these humble homes in Northeast India? Well, the lessons are pretty powerful. First, bioclimatism works. Designing with your local climate is essential. Second, using local materials is both sustainable and incredibly effective. Third, we need to remember that people are a part of the system, not just passive occupants. And finally, these ancient designs aren't primitive at all. They are high-performance systems able to provide comfort without the massive energy bills and carbon footprint of modern HVAC.
And it leaves us with this one fascinating question. As we're all searching for the future of sustainable, energy-efficient design, maybe we need to spend a little more time looking at the past. Maybe the smartest architecture we need has already been built.